Okay. Next topic is FIR filter design. Now, what is the advantage of FIR filter? One thing we have already seen earlier, that this thing FIR filters can guarantee linear phase. You can design imposing mirror image symmetry conditions on the coefficients. So, linear phase conditions can be achieved in FIR, but same cannot be said about IIR filter. That is one advantage. There is another big advantage which is not often mentioned in books. Suppose you have got one arbitrary, very arbitrary frequency response given, digital frequency response. And therefore, its repetition, this is minus pi. Like that. Now, suppose you want to design an IIR filter. IIR filter, how do we design digital IIR filter? First, we have seen you have to go to an analog domain, design a prototype analog filter, and then come back to digital domain either by impulse invariance or by directly finding out such appropriate functions and all that and replacing S by that. Okay. But HAS, we have to have a replica of this. We have to design this in the digital domain, okay, taking just the component from minus pi to pi whatever I have, making it an analog response and then design it. But you see, while doing so, there we can design some functions like filters like Butterworth filter, Chebyshev filter, Bessel, Thomson, all that. But those filters have got very specific form, like these are a form of this kind, S by okay, or equivalently suppose this is omega h by 2n. Now, you see, if you have got a very arbitrary kind of response and you want to design a filter whose frequency will be like that, you can never match it by very nice functions like this. This will be, as I told you, it will be a low pass filter like that. Another function could be another type of low pass filter, very smooth kind of function. If you have so much of zigzag, so much of random fluctuations and all that in your response, and still you want to realize it by a filter, you cannot design as such an analog filter by one of those four, Butterworth, Bessel, Chebyshev, and etc., which will be such, which will have this kind of very random fluctuations. Okay, very arbitrary kind of response. The only way to go about is then directly go for frequent FIR domain. In FIR case, suppose I take this, I sample them very close to each other, I sample. So, those will be my DFT. Sampling period is 2 pi k by n, n I take to be very large, use them, okay. N number of coefficients n very large, 2 pi k by 2 pi by n is very small. So, they are almost adjacent side by side. Then, if I take the corresponding in IDFT, inverse DFT, I get FIR filter Hn. Okay, Hn, response of Hn, if these are very close to each other, response of this Hn will be almost like this. Okay. Only thing is, only problem that you face here is that you have got too many coefficients n. So, therefore, per output yn, the convolution will be H0 xn, H1 xn minus 1 plus dot H. So many multiplications. So, per output at every index n, output will require computation output will require too many multiplications. Okay. In fact, because you have the order large, this is the problem of FIR filter. Typically, to obtain the same response as that of an analog filter, you need to have a FIR filter very large order, or to match any kind of arbitrary response, you need to have a large order. And in that case, when you carry out the convolution, you have to do, you have to have so many multiplications, means computational complexity will be high. So, this is one price you have to pay, but then here you have the advantage that you can construct a filter whose frequency response can match any arbitrary kind of frequency response, something that is not guaranteed in the case of IIR filters. Okay. In this class, we will consider FIR filter design by a very popular technique called windowing technique. Suppose you start with a very ideal low pass filter. I am considering the magnitude part only. Phase part, suppose we are assuming to be 0, or otherwise phase is linear, you can add a phase component. I will deal with just magnitude part, assume phase to be 0, say H d it is by j omega. D for desired, this is my desired low pass filter, absolutely fine. I am doing the pass band, it is flat, or outside the pass band it is 0. So, it is abruptly falling to 0 and staying there. Okay. If I really want to find out H n, if I have to take inverse DTFT, suppose it is height is 1. So, 1 e to the power j omega n d omega, and if you integrate, it will be what, j n, okay, e to the power j pi n minus e to the power minus j pi n. So, it will be 2 j sin pi n, okay. 2 j sin pi n, okay. J cancels, 2 cancels. So, sin pi n by n by pi n, pi is here, n is here. So, basically sin pi n by pi n. Okay. So, this is a sinc kind of sinc function, sinc pi n. So, you see this is going in both directions, sinc function, all right. So, it is a non-causal filter and IIR theoretically going up to infinity, minus infinity, infinity. Okay. That is because if you have got such abrupt discontinuities, you cannot realize it by using just a few filter coefficients. There is finite number of filter coefficients and a summation like this, that is n minus 1, because this summation is a finite summation and it is a continuous function of omega. Okay. Only if you bring in infinite summation, discontinuities can be realized, but if it is a finite summation, we all know it is a continuous function of omega. So, you cannot. Okay. So, this ideal filter we cannot realize because it is firstly IIR, it is non-causal. Okay. But what I can do is this, let me call it HDN, D for desired, HDN. HDN is the inverse transform of, in fact, I have taken this kind of shape, it could be any shape, that is why HD to the power j omega is your desired response, corresponding HDN is here, and this is IIR. What I will do, I will take it only over a zone 0 to maybe some n minus 1. So, that means, if I multiply HDN, I take all the samples as it is only over this region, outside it will be all zeros. That means, I design one window, rectangular window, all taking value 1 up to this. So, HDN which comes by inverse Fourier transform of whatever be the desired response, here it was this, it could be anything, any desired response, let us call it HDN. That is why I am not sticking to this form, because HD to the power j omega could be anything else, not just this. So, when I take its inverse transform, it is in general IIR, but IIR filters I am not bothered, neither I am bothered about, neither I am interested in non-causal designs. So, I apply by multiply HDN by a window WN. That means, only these coefficients, only coefficients of HDN at these points will get multiplied by 1. So, they remain as they are, otherwise they will be 0. Okay. So, I am approximating, rather truncating the original HDN to the right of n minus 1 and to the left of origin to 0. So, it is an approximation. So, obviously, if I call it new Hn, response of Hn will not be same as what the response of Hdn was, because there is an approximation. But then what will be the response of Han? Let us see this. Now, maybe I have done it in the very beginning, or I have not done, I am not sure. So, that is why it will be better to look into one basic result, that suppose Xn is a sequence, it has got DTFT this, Hn is a sequence, it has got DTFT this. We know if I convolve Xn with Hn, call convolution Yn, DTFT of Yn will be product of the two DTFTs. But if I multiply them and call it Yn, then DTFT of Yn will not be convolution of the two DTFTs, it will be product of a particular type. It will not be product, that is as I told you, if Xn and Hn are convolved and you call it Yn, DTFT of Yn will be product of these two DTFTs. But if they are multiplied, then Yn, DTFT of this will not be product of the two DTFTs. In fact, we will see that it will be a convolution in frequency domain between these two DTFTs, okay, not product, convolution. So, we can work it out. This is the DTFT. Instead of Yn, I have written Xn Hn, limit in general minus infinity to infinity. One of them maybe Xn, I can write in terms of its inverse DTFT formula. And you want to find out the output DTFT at a small omega of your choice. So, omega is fixed. So, you cannot bring another omega within integral as a variable. So, I bring x e to the power j theta, not omega, e to the power j theta, e to the power j theta n. Instead of omega, I bring theta, d theta. This is the inverse DTFT of Xn. I do not bring omega here because omega is fixed from outside. So, you cannot use it as a variable within an integral. So, this is your Xn, inverse DTFT relation for Xn, and then remaining as it is Hn e to the power minus j omega n, and now integral is a summation, this discrete summation. So, you can interchange the two, that will give rise to this is independent of n. So, it will remain outside the summation involving n, and this is summation that goes in n minus infinity to infinity, any quantity which is n will be inside this summation. So, Hn e to the power minus j omega n e to the power j theta n. So, it will be Hn e to the power minus j omega minus theta n, this summation, and d theta as it is. But this is what? This is the DTFT at omega minus theta. So, then this gives rise to this relation. This is a kind of convolution, not exactly convolution, but kind of convolution, because capital X you write not as a function of omega, write as a function of theta, and the other one you first make it a function of minus theta and then put plus omega to that. Okay, that is, you flip it and then shift it by omega and then multiply, and then after multiplication you are not calculating the area under this from minus infinity to infinity. That is the difference here, from minus pi to pi only, and multiplied by 1 by 2 pi. So, this is a kind of convolution, but there are these changes in the, remember here the limits are from minus pi to pi, and there is a product, there is a multiplication factor 1 by 2 pi outside. All right. Now, I am multiplying this Hdn, original in general IIR sequence, which is the inverse transform of a given response, any given response Hdn, that I am multiplying by the rectangular window, this is a rectangular window, okay, of length n. So, that only these samples of Hdn are retained, others are 0. So, what will be the DTFT of this product? It will of course not match the ideal one, desired one, but what it will be? So, by the previous result, it is a product of two sequences. So, DTFT of this will be convolution between the two DTFTs here, but convolution of this form minus pi to pi, not minus infinity to infinity. Okay, H d e to the power j theta and W e to the power j omega minus theta d theta. This is the formula. Okay. What is W? What is this function? What is W e to the power j omega? W n I know is this. Sorry, W e to the power j omega. It will be n equal to 0 to n minus 1. 1, 1, 1, 1, 1, so all are 1. So, no point in putting 1 here, just e to the power minus j omega n into 1. And if you go on summing, it will be e to the power minus GP series. Take e to the power minus j omega n by 2 from top and e to the power minus j omega by 2 from bottom. So, it will be e to the power plus j omega n by 2 minus e to the power minus j omega n by 2. So, it will be twice j sin omega n by 2 and it will be twice j sin omega by 2. So, it will be this into this part. Let us see how it behaves. This will be a phase. All right, this will be a phase. So, how it behaves? Then we will put that back in this integral and see. At omega equal to 0, it is 0 by 0. Sin 0 is 0, sin 0 is 0. So, apply LaHospital. So, differentiation of the numerator, denominator, differentiate with respect to omega. So, it will be n by 2 on top and by 2 here. Okay. And then cos here and cos at omega equal to 0 is 1. So, it will be n by 2 by 1 by 2. So, it is n. Then look at the numerator only. Numerator is a periodic function. Okay. It will have first 0 crossing when omega n by 2 is at pi or omega is 2 pi by n. On this side minus 2 pi by n. Second 0 crossing at 4 pi by n. Here minus 4 pi by n dot 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 dot. So, if the denominator is not present, this will go on. It is a periodic function of constant amplitude. But you see, as omega goes from 0 to pi by 2, 0 to pi, it will be from 0 to pi by 2. Sin increases, is a positive. Sin theta, for theta equal to 0 to pi by 2, because omega will be up to pi. You know, DTFT is from minus pi to pi. So, it is up to, suppose I am going in the positive direction. So, it will go only up to pi by 2. So, 0 to pi by 2, first quadrant. In first quadrant, value sine of an angle, that value goes on increasing from 0 to 1 as angle increases. That means, as omega increases, denominator is increasing in magnitude. On the positive side, on the negative side, sine of omega n by 2, omega is negative. So, it will be minus of sine some angle and denominator also minus of sine some angle. So, minus minus cancel. So, it will be the same thing, but denominator is increasing as magnitude of omega starts increasing from 0 to pi. As a result, amplitude of this numerator oscillation, which is as a periodic sine oscillation, pure sine oscillation of constant amplitude, that will continue to get damped, its amplitude will go down. That is why it will also be like sink. It would have been like this, you know, like this, like this, like this, but that will not happen now. It is getting like this, amplitude will get attenuated, damped. Okay, these are stuff. If capital N is large, this will become closer, this height will go up. Okay. Every 2 points they will come close to each other. But what happens in this case, these peaks of these side lobes, these are called side lobes, peaks increase. peaks increase, so the area under them remains same. That is a property, it can be shown. All right. Now, if I bring it back here, so this is symmetric. So, this function is nothing but, if you want to carry out the convolution, means you have to multiply the two functions and integrate from minus pi to pi. 1 by 2 pi is just a scale factor. So, h d e to the power j theta w e to the power, you can write minus theta minus omega. Okay. Minus within bracket theta minus omega. What does it mean? How to convolve h d e to the power j theta? So, this function you write as a function of theta. Okay. Okay. The other one is a function of this kind, this function. So, this also you write as a function of theta and then flip it, instead of w to the power j theta, make it this. That is a function of theta, which is nothing but, it is just the flipped thing, w e to the power minus j theta. But you see, this is a symmetric function. So, if you flip from the flip it, that is left hand side goes to right hand side goes to left hand side, it remains same. So, after flipping it remains same, and then, and I am making it narrow now. Then in general, we will be shifting it by omega. If omega is 0, I have got e to the power j minus theta, which is f of theta. It is now theta minus omega. So, f of theta minus omega. So, this will be shifted to the right or to the left by omega. So, first start with omega equal to 0. So, you want to find out the output at 0 omega. That time you multiply this function with this function, whatever be the value you get, this much you get. Now, you keep shifting to the right. As long as this main part remains under this umbrella, constant height, area after the product will remain same. So, you will continue to get some constant figure. But after a while what will happen? Maybe a positive part will come out, positive part of this will come out like this. So, if this positive part comes out, then from the previous total value, some positive amount, because it was positive part into this height, that contribution will go out. So, total value will go down. So, it will, this value will go down. After that, a negative part will move out. Okay. After that, a negative part will move out. But negative part means, as you have seen here, this height is larger than this height is larger than this height. Okay. So, amount of contribution that goes out, some positive part goes out, the negative part. So, larger part goes up, okay, negative part. So, overall earlier positive part went up out, so overall contribution, overall value came down. Now, negative half goes, you further slide to the right. So, this part also goes to the right. Okay. Some negative contribution goes out. So, it will go up. Then again further slide to the right, a larger positive part will go up. Okay, this part. So, it will again go down. So, it will be having an oscillation like this. After some time, this will come here. This is going in this direction, right. So, this will come here. The moment this will be like this. The moment this goes to the right and starts sliding, a huge chunk positive chunk will go out. So, value will come down rapidly. So, it will fall. And then again from this side maybe a negative part will go down further. Okay. So, it will go up, then a positive part like this, because of these parts also. Some first a negative part goes up, so value goes up, then positive part goes up, value goes down, something like this. Same on this side. Drawing may not be good for drawing, correct drawing you see the book, but it will be an oscillation like this. So, it will not be exactly this, but there will be these oscillations. Okay. This oscillation is called Gibbs oscillation. Okay. Gibbs oscillations comes from Fourier series. In classical Fourier series, suppose you have got a function, a periodic function f of period t, say small t, this is minus t by 2 to t by 2, the function t. Okay. You can break it into fundamental, first harmonic, second harmonic and all those things. So, typically if period is capital T, you define the fundamental frequency 2 pi by t as omega naught. In classical Fourier series, you break it as C n e to the power j n times the carrier nth harmonic this. Okay, n goes from minus infinity to infinity. This classical Fourier series, that is n equal to 0, then n equal to 1, n equal to minus 1, n equal to 2, n equal to minus 2. So, you have got first harmonic, second harmonic, minus first, minus second, like that. If you take all of them, add all of them, you get back your stuff. But suppose you take C 0, C 1, C minus 1, C 2, C minus 2, dot dot maybe up to some C p, C minus p, larger ones, and then do not take any more. What will happen? If you add them, the resulting thing will match this part, because this is a low frequency part, there is no oscillation. So, and I am considering only the low frequency, first n equal to 0, so that is DC, n equal to 1, just e to the power j omega naught t, frequency omega naught, then 2 omega naught, 3 omega naught, like this. So, the low frequency part, whereas high frequency part is present here, where there is an abrupt change from high to low immediately. So, high frequency components are locally here. So, this part will be largely mismatched by a summation taking only from minus p to p, because those high frequency components will not be there. Therefore, here we will have deviation from this. In fact, we see oscillations. If we do not take those additional components, there will be oscillations. This is called Gibbs oscillations. Here, what is the connection? DTFT as such, suppose this is the thing, DTFT. Original H d e to the power j theta, this is some H d n e to the power j theta n. Okay. But H d to the power j theta is a function of theta, but we know it is a periodic function. DTFT is periodic over a period 2 pi, okay, over a period 2 pi. So, it is like it was a function of t, now it is a function of theta. So, what is the fundamental frequency? That time it was 2 pi by t, now it is 2 pi by 2 pi. This period is 2 pi, that time it was t, it is 2 pi. 2 pi by t there, 2 pi by 2 pi here. So, omega 0 fundamental is 1. Okay. And n times you can write this way also, H d you replace n by minus n, it is j n theta. Okay. N you replace by minus n, so it should be from plus infinity to minus infinity, but does not matter whether we start from plus infinity to minus infinity or minus infinity to plus infinity. Number of points you covered in the discrete sum is same, whether go from left to right or right to left. So, you can again write is this. So, this is actually the Fourier series expansion of this. So, discrete time Fourier transform DTFT expansion is nothing but a classical Fourier series expansion of this periodic function of theta, where you have this is the Fourier series coefficient for n times the fundamental. Okay. It is equal to j n into 1, 1 was the fundamental. So, n times fundamental, there is nth harmonic, theta is the function, this axis is theta, like this axis, nth harmonic, its corresponding coefficient is h d minus n. Okay. You can give it any name, h d prime n, whatever, and it goes from minus infinity to infinity. Now, in this filter design, from this desired thing HD 0, HD 1, HD 2 and all that, HD minus 1, I am selecting only a few, HD 0, maybe HD minus 1, HD minus 2 like that. So, HD minus 1 means HD, okay, minus 2 like that, a few of them, and I am throwing in others. As a result, when I add them on the right hand side, as long as the low frequency part is concerned versus theta, the oscillation variation versus theta, the low frequency part is concerned, this will be matched, but there is an abrupt transition, okay, from high to low, that reflects the presence of high frequency components. There we will have this oscillation, there is mismatch, and that is what you see here, this Gibbs oscillation. Okay. This is to minimize this Gibbs oscillation. What they do then, instead of taking a rectangular window, they take a window which is not so abrupt. This rectangular window was abrupt, either 0 or 1, 1, 1, 1, 1 and then 0. They make it smooth, like maybe in a triangle, it is triangularly modulated, maybe this. So, goes like this, like this. This one, it could be sinusoidally modulated, 1/2 of sinusoid. So, here you multiply HDN samples, HD 0 by this, HD 1 by this, HD 2 by this, like this. Here HD 0 by this, HD 1 by this, HD 2 by this, like this, and you get better performance in terms of this ripple. Okay. So, that is all for the windows. These various windows have been devised. If you see Oppenheim's FIR or ProEQS and others, you will see various window functions are given, Bartlett window, Hamming window, Hanning window, Kaiser window and so on and so forth. They are very famous windows. So, this is for FIR filter design via windowing techniques. Thank you very much.